So in this video we will talk about a binomial distribution and how can we represent the binomial probability in a recursive manner. Okay, so by definition a discrete random variable x is said to have a binomial distribution with parameters n and p if the probability of x is equal to x given by this n choose x p to the x 1 minus p n minus x. Okay, so this is well known. Okay, but the question is that imagine that um, you have to generate binomial numbers for a large n. So if you use this formula, then we have a factorial representation of n combination of x. Remember that this guy is n factorial divided by x factorial times n minus x factorial. So if n is very large, then this guy is very computationally exhaustive to calculate. Okay, so what we are trying to do here is to find a recursive representation of this probability. So now in actual what we will do is we will do this. We'll say the ratio between probability of x is equal to x versus probability of x is equal to x minus 1. Okay, so again, but what we will do here, we will just apply this definition to both of them. So this is n choose x p to the x 1 minus p to the n minus x. The denominator is what? N choose x minus 1 p to the x minus 1 1 minus p to the n minus x plus 1. Okay, now let's consider each pair separately. So what is n choose x divided by n choose x minus 1? So this is equal to n factorial divided by x factorial times n minus x factorial divided by n factorial divided by x minus 1 factorial times n minus x plus 1 factorial. This is equal to n factorial over x factorial n minus x factorial times x minus 1 factorial times n minus x plus 1 factorial divided by n factorial. So this n factorial and this n factorial cancels out. This x minus 1 factorial cancels out with this factorial. Why? Because x factorial is what? X times x minus 1 factorial. And similarly this n minus x factorial cancels out with this n minus x plus 1. So I am left with what? I am left with n minus x plus 1 over x. Okay. Now what is this guy? P to the x divided by p to the x minus 1. So p to the x divided by p to the x minus 1. This is equal to just p. What is 1 minus p n minus x divided by 1 minus p n minus x plus 1? So 1 minus p to the n minus x divided by 1 minus p to the n minus x plus 1. This is equal to 1 minus p to the minus 1. So then if I combine this guy and this guy, I get p over 1 minus p times n minus x plus 1 over x. So in other words, I can say px is equal to x. This is equal to p to the x is equal to x minus 1 times p over 1 minus p times n minus x plus 1 times n minus x plus 1 over x. Okay, so this means that we can define every next probability in terms of the previous probability times something, but we need an initial condition here. So binomial distribution starts with, so x, what is the range of x? X is the in range 0, 1, 2 up to n. So what is P of x is equal to 0? Sorry, x is equal to 0. This is equal to, you put 0 here. So n, choose 0 is 1. P to the 0 is 1. And 1 minus P, n minus 0 is 1 minus P to the n. So this is equal to 1 minus P to the n. So this is my starting situation. So P, probability of x is equal to 0 is 1 minus P to the n, and then I can use this recursion to find the probabilities of my subsequent integers. Okay. So now how is it useful? So to see the use of it, what we do is we go to MATLAB, for example, and MATLAB is not necessary. You can use any computational software to check whether this reduces computational exhaustiveness or not. Okay, so this guy says that we have some n, p, and x defined, n and p defined. Basically, we want to plot our numbers generated from the binomial distribution through the formula and through the recursive definition. So just as a demonstration, for the formula we just use exactly the same formula, and n choose k and n times p to the n times 1 minus p to the n minus n. And for the recursion, we do what we have. If the initial condition is true, then we say our answer is 1 minus p to the n. Otherwise, it is this factor which we just calculated times the binomial number formed from the previous version here. Okay, so now here what we do is we choose n is equal to 40 and see what are our results. So you can see that we have two graphs which are same graphs, but the time elapsed for the first one was for binomial formula, and second one was for the recursive formula. Time elapsed for the first one less than double of the time taken for the recursion. But now let's increase our n to maybe 150 and see what happens. When we increase our n to 150, we see that for the increase our time, when we increase our n to 150, we see a huge difference. So this is about 100 times less for this n. And also, not only that, the software starts to complain that for this huge factorials, it needs more memory to store. Okay, so for normal integers or for normal floating point numbers, it does not have enough memory to store the huge factorials for this. But there is no such warning for recursion. So here, imagine that you are writing a program in which you have to generate these numbers in a degree of let's say in the order of 1000 or in the order of 2000. So in this case, a formula like this is extremely helpful. So it will save some computational time and it will save some computational resources for you. Okay, so this is it for a straightforward derivation of how we can generate how we can represent binomial probabilities in a recursive fashion and what is the use of it. Okay, hope it was easy to understand, and thanks for watching. Hope you liked the video.